Okay, guys, we're going to do 10.6, which happens to be the last lesson of the chapter. So next week, you will have the review, the reflection, and the test. Okay? So it shouldn't be too bad. And then we're going to, I think, jump ahead to chapter 12 after that. We'll see how things go. So we're talking about geometric probability, and I actually hate probability, but I can totally get behind geometric probability. Like this to me makes way more sense. So hopefully this isn't too difficult for you guys either. Remember that in probability, the set of all possible outcomes of an experiment, that's called the sample space. And any set of outcomes, this is called an event. If every outcome in the sample space is equally likely, the theoretical probability of an event is, and here's probability, equals number of outcomes in the event over the number of outcomes in the sample space. So, what you want over all the possibilities. Geometric probability is used when an experiment has an infinite number of outcomes. In geometric probability, the probability of an event is based on a ratio of geometric measures such as length or area. The outcomes of an experiment may be points on a segment or in a plane figure. And these are the three things we're going to talk about today. Length, which is probably, I don't know, depending on, this one might be the hardest of all three. And it's not that hard, but that's what we'll start with. We're going to talk about angle measures, the probability on that, and then we're going to talk about the area of a figure. Okay? So the length, you just take this part divided by the whole thing. Angle measure, you would take a certain degree divided by 360, and the area, you'd take the area of a figure divided by the area of the whole thing. So let's just get through this. A point is chosen randomly on PS. Find the probability the point is on RS. Okay, so this is the part we want, 5. And we just need to put it over the total amount, which is 25. Because we got 7 plus 13 plus 5. And I'll just reduce that to 1/5, or 20%. Using the same figure, find the probability that the point is not on QR. So we need this plus this, because those are not on QR. So we have 7 plus 5, which is 12, over 25. Using the same figure, find the probability that the point is on PQ or QR. Okay. So now we have PQ or QR. So we need 7 plus 13, or 20, and it's still over the total number on there of 25. Oh, why does it do this? I hate that. There. So where was I? 20 over 25. Or 4/5, or 80%, or 0.8, however you want to write it. Let's look at this walk stuff here. A pedestrian signal at a crosswalk has the following cycle. Walk for 45 seconds and don't walk for 70 seconds. What's the probability the signal will show walk when you arrive? So this is what I do. I usually draw this out into a segment, and I do, it won't look even, but this is my walk for 45 seconds. And then I have my don't walk for 70 seconds, which means my total is 115 seconds. And the probability that it will show walk, that's 45. So 45 over 115. That looks like it reduces to 9 over 23. And you can figure out the decimal of that if you'd like. This one here, I believe, is the most difficult one of all, and it's not that bad if you draw it out right. So we're still using the same pedestrian signal crosswalk thingamabobber. If you arrive at the signal 40 times, predict how many times you have to stop and wait for more than 40 seconds. So if you think about this, and I'm going to draw it maybe a little bit differently. I'm going to draw the walk on this side for 45 seconds. And then here's my don't walk for 70 seconds. And how long would I have to wait for more than 40 seconds? Well, if I have 40 seconds in here, and anything more than that would be 30 seconds, then I'm going to have 30 out of 115. And well, that happens to reduce to 6 over 23. But that's just for one time. And it says if you arrive at the signal 40 times. So all you need to do is multiply this by 40. When I do that, I think I get like 10.43, blah, 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 blah. So it says about how many times will you have to stop and wait more than 40 seconds? Well, about 10 times would be your answer. Let's look at the spinner for these questions. It says use a spinner to find the probability of the pointer landing on yellow. So I have 140, and I just need to divide by 360, which reduces to 7 over 18. It's the probability of it landing on yellow. How about the pointer landing on red or blue? Well, red is 60 and blue is 52, so I'm going to take 60 plus 52 and put it over 360. That's the total number of degrees in that circle. So I have 112 over 360, which reduces to 14 over 45. And the pointer not landing on green, so that's everything but the green. So 360 minus 108, which is going to be 252. And I'm going to put that over 360. And it looks like if I reduce that, I get 7/10. Or 70% of the time, it will not land on green. I know I'm going through this quickly, but I don't think this is anything crazy new for you guys. Let's look at the last part here where we're using the figures to find out the area. So it says find the probability that a point chosen randomly inside the rectangle is in each shape, round to the nearest hundredth. So I like to think of this as, because I am not very athletic, if I throw a dart and it's going to hit, it can only hit within this rectangle, how many times will it hit within the circle? And then how many times will it hit within the trapezoid? Or what's the probability, I guess I should be saying. So first you need to figure out the area of the rectangle. So the rectangle, you're going to have 50 times 28, which is 1,400 feet squared. Okay, that's the rectangle, the whole thing. Then we need to find the area of the circle, and then we'll divide it by the area of the rectangle. So the area of the circle, we need radius, so that's 9 because the diameter is 18. So radius squared, 9 squared is 81 pi. And then we'll just divide that by 1,400. And I get about 0.18. So the probability, if I was throwing a dart, I would have less than a 1/5 chance of hitting in that circle. The trapezoid, now that should be a little bit more of a chance because that's taking up a little bit more of the area. So I will find the area of the trapezoid, which, in case you forgot, you have to add your bases and multiply by your height and divide by 2. So my bases are 34 and 16. And my height is, now this is tricky, make sure you know that your height is 18. Don't use this 28. When I multiply, okay, so that's 50, so it's 25 times 28. I get 450, I believe. So that's the area of my trapezoid, 450 feet squared. And I just need to divide it by the 1400 to get my probability, which is 0.32. So about 32% of the time, or roughly a third of the time, I would hit within that trapezoid. Let me know if you have any questions.